This is my interview with Rich Sutton, and I will leave a time code right here in case you want to jump straight into it, but I would be remiss if I did not give this man the introduction he deserves. Rich is probably the single most influential person in the field of RL. I mean, he wrote the literal textbook on the subject, and he is still working on RL research as a professor right now at the University of Alberta. And Rich does a number of things beyond that. He is currently the chief scientific advisor at OMRI. He recently co-founded the OpenMind Research Institute, affectionately known as OMRI, where he works on a lot of his cool ideas. And even more recently, he started working with John Carmack's AGI startup, Keen Technologies. And that alone is a lot. But to me, Rich is a lot more than that. He is both a friend and a teacher I have learned so much from. Rich comes at research with a very different perspective than pretty much anyone I know, and I hope that's something that shines throughout the interview and something that maybe my viewers will appreciate. He certainly has a lot of unique ideas and opinions that you'll hear. And the last thing before we get into it, I want to give a big thanks to OMRI for sponsoring this video. They provided both the venue and the equipment to make this happen so I don't have to record on my iPhone like I'm doing right now. Whether you are a student that wants to find a community for RL, or if maybe you run a company and you're looking to hire an ML contractor, or whatever you want to do with ML, OMRI probably has you covered. They do all sorts of ML stuff, and as an OMRI community member myself, it is incredibly easy to endorse them. I'll leave a comment in the description if you want to learn more about them. The interview is fully annotated, and because I haven't interviewed anyone before, I get started off a little bit awkward, so sorry about that, but feel free to jump around as you see fit. And with that out of the way, I hope you enjoy it.
Hello, Rich. 6 months in the making. This suddenly feels way too formal. So let me introduce you. I think there's probably no better place to start than OpenMind Research Institute. This is like open now, right? We can talk about this?
Yep.
Okay, so I kind of know because I was just at the retreat. What's happening right now? So I guess you're starting to recruit people to work on stuff, to work on the Alberta plan?
OpenMind Research Institute is a part of our ecosystem. It's part of our effort here in Edmonton to push artificial intelligence, learning-based artificial intelligence, and in particular reinforcement learning-based AI. And there is a need both for additional, research funding. The OpenMind funding is very unrestricted, and it's separate from the university, and it's explicitly for young scholars. So we're going to make a whole series of fellowships, 5 to 10 fellowships, which will just run on an ongoing basis, and they'll support. It could be people from anywhere in the world. They don't have to spend all their time in Edmonton, actually. We like it if they come here and get to know us. And we'd like to work very collaboratively. But, it's just, not just at all. I always be suspicious of that word just. It's an attempt to push the research in all the fundamental directions it needs to go. Okay.
It needs to go. Okay. So it's kind of hard to talk to you and also talk to the audience at the same time because I feel like I have an idea of what you mean by the directions it needs to go. But you definitely have a very strong opinion on,
I like to think of it as the Alberta viewpoint.
Oh, yeah.
And so we call our document the Alberta Plan for AI Research. And it's admittedly a bit different.
A bit, very, in interesting ways,
Yeah. To me, it makes sense the way to do things. You should do learning. You should do scalable methods. You should focus on the learning algorithms and try to get them just right. You want to do both real-time interactive learning and planning, reasoning. It's not the usual deep learning kind of thing. But we're not against deep learning.
Yeah.
I myself, you said I've been here a long time. I've been doing this kind of work a long time. It's like 45 years, a long time. And I've seen a lot of things come and go. And 3 waves of neural networks.
3 waves of neural. Oh, I guess, so you have like the AI summers and the AI winters. Yeah.
Well, no, the neural network phases are separate from the AI phases.
Okay.
I mean, they're uncorrelated, I think.
So what were the neural network phases like?
The first one was in the 60s.
Okay.
Was the perceptron.
Okay.
And
Perceptron.
the Woodrow-Hoff rule and the Adeline and the Informon. There are a whole bunch of neural network things.
Cool. So it's just like today with all the LLMs, where they all have very weird, fancy names, maybe named after Sesame Street or the equivalent in the 60s.
They were classic, I always say connectionist because they were neuron-like, but they're not neurons. Anyway, these things, associationist, numerical, statistics related, the perceptron, 1958, and thereon. So then then learning became extremely unpopular in AI. It was actually, no one did it.
Yeah, so that was like the knowledge systems, expert knowledge. That's when that became like a big thing, right?
And that's when I came of age as a student. And I just felt out of place because I was really psyched to do learning, and no one was doing it. It was totally out of place in AI. And then it became super popular again in the 80s, late 80s. Mm-hmm. And then there's the most recent one that we know is deep learning.
Yeah.
3 separate phases, not that different of ideas.
Yeah, it is interesting when you look back at lots of, I think, recent successes. Lots of them do seem to basically take past really successful ideas and then they take neural networks and deep learning and kind of, not all of them, but that does seem to be, how many new ideas?
We could just say simpler, it's scale. It's computation.
Yes.
It's Moore's law.
Yeah, so I actually made a Reddit thread asking people what I should ask you. I'm not going to ask you lots of those questions because some of them were like, ask them about Q-star, which don't worry, we're not going to talk about. But one of them was reflecting on the bitter lesson. So that got a lot of upvotes, but I don't know, I think the answer is pretty obvious. It's pretty obvious that that's right, that scale is even now more important than ever, right? So scale is what's changed. Okay, so this actually leads really well into a question I wanted to ask you though. So something you said was that scale is easy. It is easy to scale things. This does not compute for me. How, now, I guess if we're trying to break things into the 2 categories of like coming up with new algorithms or new ways of doing things and then scaling them once you have an idea that they work, coming up with new things is hard. Why? But scaling also seems like it would be hard to me, like backprop, right? Backprop, I guess, came around quite early, but maybe started being used in neural networks in like the 80s. And it took like, I guess until today to work out, not until today, I guess, it took time, right? To get it to work on larger networks. I mean, part of that was probably just like not having the compute. But I imagine that there were problems with it in the beginning that have been worked out over time. I think I'm just going in a really roundabout way to ask you, like, why do you think scaling is easy? I think lots of people would disagree. Well,
I don't remember saying explicitly that, but
okay.
But it does sound like something I might say.
Okay.
And it just seems like a truism, to make up some new way of interacting, a new algorithm versus scaling it up to replicating it, making it bigger. Not making it bigger, you make the network bigger. Like that is not conceptually challenging.
It's not conceptually challenging.
And it's not harder to make bigger arrays and stuff. It's, of course, you have to have, it all becomes more complicated because there are more parts moving and you think more things to keep track of. And, but still, all those things, to me, they fall on the easy side as opposed to making some new thing that we don't know how to do yet.
I guess it's kind of fair. I don't know. I'm having a hard time accepting that scaling would be that easy. I think both are hard, specifically because not everything's going to scale, right?
Then and that's the problem. Is not with the scaling. It's with the method that doesn't scale.
But how do you know that it's not going to scale? Well, some things it's obvious they're not going to scale, right? But other things it's probably not so clear, right?
I guess you're saying that things may not scale. But if they scale, then the scaling is easy.
Okay, so if they scale, the scaling is easy. Maybe, I'm more willing to accept that. Okay, but then there's still like the search for like what's going to scale, what's not going to scale. Anyway.
Yeah, we want to find methods that will scale. And that's the hard part.
Yeah.
And and I would say we haven't done very well at it.
Okay, so
you can't blame people for not succeeding, but I do blame people for not trying. You know?
Oh yes, get the spicy opinions out there, please. Yeah. So
So I was thinking a little bit about that today. Just like there's all the major things that are interesting and challenging algorithmically. Like no one's working on them. They haven't worked on them for decades. Like representation learning or generalizing well, abstraction in state.
people work on that.
I would say that when backprop was first made in 1986, they created the meme that, backprop solves representation learning.
This is what I was just going to ask you about. So perfect segue.
And it's just not true. But it's bad because they said that it solved representation learning, so people didn't. It makes it harder for people to work on it because it's already been solved. And so why would you work on it? And if you were working on it, you'd have to write the introduction and say, first change everything you thought, and then I would have the motivation for my work. Instead.
Okay,
it really ruins it when people say they've already solved it.
Okay, let's start with why do you say backprop does not solve representation learning?
Well, we know what backprop does. Backprop is gradient descent. So backprop will, it'll adjust the weights to solve the problem.
Yeah.
But it doesn't adjust the weights to find a good representation to solve the problem.
So what determines a good representation? Is a good representation not the one that helps solve the problem?
Well, so it's kind of a minimal requirement. You want to be able to solve the problem, but that's not. So that's not what I think. Well, it's not what I mean by a representation, by a good representation.
So
yeah,
I'm gonna hit with a hardball here. Is that not sort of what the whole sort of area of self-supervised learning is trying to do right now? So there's kind of this lots of hot takes recently about that RL is not very important. No, these are not the hot takes. These are the normal takes. We're the people with the spicy takes. So there's lots of people that will say, right, RL is nice to have. It's important as maybe the final step, quote, the cherry on top. I'd imagine you've heard this. And the idea is that lots of what we want is really in the self-supervised phase where you don't necessarily have any sort of reward signal or anything like that, but you just learn from the structure of, in lots of cases it is supervised learning, but there's no reason to think that you couldn't have similar things in like the sequential decision-making process, right? Where you learn about the structure of transitions, what the state looks like, how you achieve certain goals that are not at all related to the reward. I do think people are working on that.
Well, those of us in reinforcement learning are directly working on that. So I don't see that as opposed to reinforcement learning at all.
Oh, not opposed, certainly not. But
so let's say more precisely what you are saying in the name of those critics. The critics are saying there's more to learn about than just the reward signal.
Yeah.
And maybe the reward signal is actually just one little signal. There's many more other things to learn about than there is reward.
And I'll add one thing to that is that if we learn those other things, perhaps then it will be easier to learn to maximize the reward later.
Well, whatever.
Okay, sure.
We want to agree, you want to learn about those other things, and they're the largest source of information. And, many things. So So for me, reinforcement learning is learning that pays attention to the actual structure of the data. And so the reward part says, well, the structure of the data doesn't tell you what to do. It just tells you how good what you did was. But the other very important part of the data is there's lots of data other than the reward, and you will have to utilize that. In some sense, temporal difference learning is about using other signals to allow you to predict reward. And anyway, a major area within reinforcement learning is model-based reinforcement learning. Another major area is general general value functions, and all these things are just exactly making this point, that you do predict other things than the reward.
Yeah.
You want to make a model, and you want to predict many other things. So in my opinion, the field of reinforcement has worked much more on predicting other things than other fields have. Okay, so other parts of AI have. Yeah. So let me explain that.
Past the hot take. Yeah.
So
okay.
what you'll find outside of reinforcement learning is lots of guys trying to predict the next observation or the next video frame.
Yeah.
Okay, and their fixation on that problem is what I mean by they've done very little, because the thing you want to predict about the world is not the next frame. You want to predict consequential things that matter, things that you can influence, and things that are happening multiple steps in the future.
Yeah.
Okay, so let's not. I don't really like playing it out as slams. He slammed me and I slammed him. Maybe that's what you mean by spicy, and maybe you think that's fun. But it's sort of a good backdrop anyway. But what would be a more neutral way to observe what's happening? So I would say it's that we all are facing the truths of the problem. The problem is that you have to interact with the world, you have to predict and control it, and you have large sensory motor vectors. And then the question is, what is my background? Well, if I'm a supervised learning guy, I say, maybe I can apply my supervised learning tools to them. They all want to have labels, and so the labels I have is the very next data point. So I should predict that next data point. It's a perfectly constant way of thinking, consistent with their background. But if you're coming from the point of reinforcement learning, you think about predicting multiple steps in the future. Just as you predict value functions, predict reward, you should also predict the other events. These things will be causal. I want to predict, what will happen if I drop this? Will it spill? Will there be water all over? What might it feel on me? And those are not single-step predictions. They involve whole sequences of actions, picking things up and then spilling them and then letting them play out. There are consequences. And so to make a model of the world, it's not going to be like a video frame. Just think about that. It's not going to be like playing out the video. You model the world at a higher level. You model, the water will be out of the cup, it'll be wet all over. Yeah. I don't know what the video will look like. I might be standing up, maybe. The video is not the way you want to predict. You want to predict it at a higher level.
Yeah.
So general value functions and temporal difference learning prediction is the key to making a model of the world.
Yeah.
Yeah, so that's what I believe. You just said, yeah, that was nice of you, but so I think that's the crux, the point of it. Are you trying to predict the very next observation, or are you trying to predict a higher level? Is it temporal difference learning, or is it supervised learning that will be predicting the events to make a model of the world?
Yeah. So
if we take some of the other people that are worrying about making models of the world, like Jan LeCun and like Yoshua Bengio, I totally agree with them. I think we're so aligned because we all agree that the key thing is to make a model of the world that will allow you to predict it and plan about it and think about it. And these are key, and this is why, for example, large language models are not really going towards the important things because they're not about forming a model of the world. I agree with all of them, but they're coming from the point of view of supervised learning. I think they probably just haven't fully ingested the power of temporal difference learning.
Yeah. Would you say you're a little bit biased, given that you might have had a little bit of a say in the start of temporal difference learning?
I'm biased in the sense that I know about it.
Yeah. Yeah. This is good, though. This is exactly sort of what I wanted to get at. Because when I discuss this with people lots of the time, sort of like why don't you think reinforcement learning? What do you have why do you have a problem with reinforcement learning? Oftentimes, there seems to be a real.
So I want to stop you right there.
Okay.
Like, why is it that people are having problems with different things? And it's not just you, but I've noticed this before. People will have slams of other points of view instead of like being scientists. And scientists would say, there are multiple approaches. I wish them luck and see the benefits and the strengths. But instead, they're sort of like,
I don't know.
no one cares about that. It's sort of like high school a little bit, instead of like science.
I think most of the good researchers are not like that. Maybe some are, but
yeah, I don't disagree with that. But still, it's part of our culture. It's part of our community.
Yeah.
It's part of our research community.
Anyway, I think we did kind of get to what I wanted to get to, which was, we really do all agree that learning about all these things learning about the world, learning about the environment are important. It seems to be more the different approaches.
So let's say,
right?
duh,
Yeah, duh, okay, yes. Yeah, I think we yes, we're all in agreement.
I've noticed this about I want to riff on this a little bit because
go for it.
Something that bugs me a little bit. That too often in our field, people find a good idea and they want to say, oh, maybe this idea is everything and all the other ideas are unnecessary.
Yeah, that does happen a lot.
Yeah. Why not say, oh, this is a really good idea and maybe this will go really well with that other good idea? No, it's one idea. So I want to give my examples. My examples are, for a long, long time, deep learning, gradient descent could do everything. And maybe that's still true. The idea that it's all gradient descent and nothing else is needed, even reinforcement learning is going to all be done by gradient descent. There was nothing more needed. Another one, it's really popular, is prediction. I'm really into prediction, and I would think that everything should be predicted. And I just feel funny when people do, as you almost did a minute ago, was to say, oh, but what about predicting lots of things? I think now you're just not paying attention, and the fact that you're not paying attention and criticizing means that, you're just not being a good critic, just not even, anyway. So prediction, I love prediction, and so I came across these other guys, the predictive coding people, they were really interested in prediction. I thought, great, these are my brothers. These guys doing the same. They see what I see, that prediction is so important. And they said, yeah, prediction is so important. It's the mistake was to do control. Yeah. And so,
oh no.
Yeah, exactly. And no, we predict so that we can control. No, they think, no, if prediction is important, then nothing else can be important. Control must be unimportant.
Yeah. Okay.
And so if predicting predicting lots of things are important, then predicting reward must be unimportant. Why don't we just say you should predict them all? Yeah, reward is a particularly important thing to predict. It's not the only thing. Anyway.
That's good. Maybe now we've kind of got all that out of the way. We can get into maybe, I kind of want to hear some of the things you're excited about now. We've established lots of things are good. There's lots of interesting ideas. You have a lab that works on a lot of different things. You have colleagues at OpenMind Research is just getting started. You have the Alberta Plan, which talks about all these really cool ideas, exploring lots of these things. But
of course, all the things I do are out of fashion.
Well,
but I could try to persuade you or your audience that they should be in fashion, or I could just tell you what I think.
Yeah. Tell us some things you're interested in recently.
Maybe I'll try to do something somewhere in between. I do think it's important to find good abstractions in state and in time, and that's one of the biggest things that are missing.
Are there any specific approaches recently that you've worked on or you're excited about, or even just you've thought of and you haven't gotten to them yet, but sound interesting?
So if you're going to find better abstractions in state, and state really means features. We don't have states, and so we form features, and we want to find better and better features. And I guess I'll just state this, which is that I don't think for all that's been done in deep learning, none of it is about finding good features. What do we mean by good features? We mean features that generalize well. We have to learn how to generalize well. That's a different goal than just solving a problem well. And so how do you find good features? It's kind of an unsolved problem. I think the first thing is to notice how good your features are. You have to. So there's learning and there's meta learning. Whenever you want to do something like find good features, so that subsequent learning is efficient. In other words, so that you generalize well. Then you're talking about meta learning.
Yeah.
Yeah, and so incremental delta bar delta is my favorite method it's my first method for learning,
good old IDBID.
Sculpting your generalization, the way you represent things and how you generalize in the future.
So that's basically about finding the features that are important and making sure you update those a lot or faster, right?
Figuring out how much you should update them.
Yeah.
So there's all kinds of step size adaptation methods in the literature, and none of them find good step sizes. They just find better step sizes than you started with. We've actually done some work recently drawing it out very particularly that methods like incremental delta bar delta, IDBID, IDBD, these methods find the best step sizes rather than, whereas if you take something like RMS prop or Atom, they will change the step size, but they won't find the best step sizes.
Yeah. So this is one thing I was never thinking about until I took your class. In the sense that I guess because I come from the perspective of I saw deep learning. It's like, oh cool, let me try applying this, figuring out how it works, and then the step size is generally something that's always fixed. I mean, not entirely fixed because you have maybe some atom optimize or something else that will change it a bit as you go. But one thing I never thought about is how much it actually affects your learning and how much it could actually potentially help when you do have an actual, you have a step size for or a learning rate for every single parameter. It seems like that should be able to have a pretty big effect.
You determines which parts of the network are changing and which parts aren't.
Yeah.
And what's a big problem today that we can't we can't continue to train our networks because the wrong parts change.
Yeah. And I guess this is kind
catastrophic forgetting.
Yeah. Lots of interference when you have.
So the view of IDBID and continual backprop is that the network pays really strong attention to which parts need to be stable and which parts should change a lot.
Yeah.
And this is a real critical decision if you determine how fast you will learn with the next input data point. Yeah, it's a really important thing, and why we would just have one step size for the whole network is sort of crazy. The only thing that changes is the weights, and the weights change by gradient descent, and it's proportional to how much effect they have. It's a really bad choice.
Yeah, it is interesting to me that it's something that doesn't get brought up much. It's something
even after all this time, we still don't pay attention to it. Instead, what we do is we say, well, we don't want to pay attention to all that stuff, and so we're just going to do batch, and we'll train it all slowly and small weights and multiple iterations, and so we can wash all that out. Instead of saying, oh, this is something we need to figure out, we find ways to avoid it. And then we say, well, if we do pay attention to it, if we do train online, then it doesn't work very well.
Because we haven't figured it out.
Yeah. I think this is a really important point, actually. The actual data is online, and it comes at us one by one, and we don't save it. That's such a strange idea that's become normalized. We don't save it, we train when it happens. And you could say it's harder to learn online But you can't say that we don't need to do it. You can't say it's hard to do that, so we're not going to do it. That's what people say.
Would you be opposed to an approach that learns online and also has some sort of batches that happen sort of, consistently in the background? I guess that's kind of what model-based like planning stuff does.
Yeah.
But then you also want the online stuff so you can update faster, right? So you can learn immediately.
You should learn the model online.
Yeah. Yeah. I guess
So it's,
you can't learn the model with the model.
yeah. So I don't want to go to replay buffers. I don't want to go to batches. I want to go online, and I want to learn my model and then plan with the model. So there's no place in there for replay buffers. Replay buffers are not even a well-defined idea. It's not a well-worked out idea. It's just something that people do. I'm referring to the idea that what do you store? Do you store the state or do you store the observation? And if you store the state, well, the state changes over time. And what is the state? Is it the whole network? There's no clear state in a normal deep learning.
Yeah.
If you store just the observations, well, then you have to run through many observations to get back the state.
Yes. I mean,
It's not a clear idea.
it's not clear, but it could be clarified, right? They're interesting questions. I mean, you could imagine the brain probably has similar issues, right? Like if you think about, it is very interesting where probably the further back a memory is, sort of the harder it is to recover that state, right? I do wonder if there's a parallel there to like how, what you were just saying, right? Your state, your representation is going to change over time. So if you try and reach too far back, you're going to end up with something that's less informative or perhaps even wrong. Yeah, I wonder if there's any interesting work that looks into that parallel. We are getting pretty deep here. This is good. This is good.
So I'll mention one thing that we're excited about,
Ooh,
which
yeah.
is kind of related to this memory thing.
Okay.
How do we decide memory? Like, it's just a word. We mean so strange things by it. So the first thing we should say, we don't know what we mean by it. So
Yeah.
then we can propose what we might mean by it. Well, the proposal is that you take a snapshot of the important state variables at a particular time.
Yeah.
So you're always snapshotting, and then what does it mean to snapshot? It means, well, you might imagine that it's a neuron-like unit that becomes active, that becomes response, takes a snapshot of that current pattern, and will respond if that exact same thing happens again.
Exact same thing or something similar?
Certainly will respond if the exact same thing
Yeah.
happens again. That will respond maximally to that, but it will also
Yeah.
respond to different degrees at other times. And so you could take snapshots of every moment that passes by you. And actually that's not particularly expensive. And you would take many snapshots and then you just forget them rapidly. So the things,
Yeah.
your storage is limited. So anything that you store, if you take rapid snapshots, frequent snapshots, then you have to forget most of them. Other ones you can forget more slowly, or you can replace them more slowly. And so then you get what you described. That the older things that you can remember longer are fewer, less precise, and detailed memory of the last second maybe.
Yeah. You mentioned this to me before. Is this something you're working on or just an idea, a floating idea right now?
Kerm Javed and I are working on it, yeah.
Is this the
This
stuff?
is what he's using in his latest demo.
Oh, okay, I see.
auditory
I might be
things.
making a video on that. So for anyone watching, that might be coming.
Really
soon.
exciting. This is, in fact, the idea of how we propose to create new representational elements
Yeah.
as snapshots of things that had happened at a particular point in time, augmenting gradient descent. Take a snapshot, that gives you a starter, and then you further refine it by gradients from there.
Yeah. And then, yeah, it's a very interesting idea. I'm surprised I haven't seen something like that explored before. It seems very simplistic, very powerful, potentially. Why are you laughing?
The world is full of such things.
It
It's just we have lack of
is.
imagination.
is.
Yeah, it's full of, yeah.
Any other good ideas I can snatch for you, or if there's any grad students watching that want something to work on that lack imagination?
Well, there's a lot of things in planning. How do you make the model? How do you build partial models? How do you learn them off policy?
So I'm very curious. What's when you come up with a new idea? What's your thought process there? So I think a lot of my early thought process in deep learning, like if I was looking at model-based learning, right? I basically look at what people currently do, and then I'd look at perhaps tweaking something, or I guess you want to find a problem of something that's not working, and then try and build out from there. What do you like? How do you come up with the ideas you come up with?
Well, that's a deep question.
Yeah, maybe that's
but it can be fun. It's kind of different, less combative.
Yeah, sorry if I'm not trying to be too combative here.
Yeah. I'm probably doing it. What are good strategies for thinking and coming up with new ideas?
How do you come up with good ideas? Because I realized when coming here, I used to be really good at coming up with ideas, and I still am. But when I came here, I realized lots of them are they're shit ideas. Coming up with good ideas is hard. How do you come up with something that has a high chance of giving some interesting results?
Well, the first answer is you come up with lots of ideas, and then a small portion of them will be good. You know that.
I'm glad to know I'm not the only person that comes up with lots of bad ideas.
So you have to, the trick is not to get stuck on a bad idea. You want to go through them quickly so you can get to the good ones.
Yeah.
The 1 in 10 or 1 in 100 that's really good. I find it critical to write down one's ideas in a notebook. I think you've heard me many times say that. So you have to challenge your ideas, and one way to challenge them is to write them down and look at them and say, now that I've written that down, that doesn't seem right. I can immediately think of 3 counterexamples. Or maybe you say, oh, that does seem like good. Let me write some more about that. So writing is good. Thinking the top level, my top level slogan for AI research is drive from the problem.
Yeah.
Yeah.
I've never heard this.
Never
This is
heard
your
this?
slogan? I mean, I've heard of variations. But
Have you heard that I have at least 10 slogans?
Oh,
exactly
10 slogans.
And they're on the internet. You could look up Rich's slogans or something.
I'll overlay them on the screen right now.
And
so
they will come
you can
up.
see them.
And unless I'm mistaken, the first one is drive from the problem.
Okay.
Then you think about the problem. That's what you should be thinking about more than anything else. What is the problem that I'm trying to solve? And so I say, well, we're trying to solve a reward problem. We're trying to make, we have this kind of sensory information. We have not just the actions, we have the observations, and we can maybe build off the observation. Anyway, drive from the problem. And so you want to think a lot about the problem and then find things that haven't been worked on so much.
I want to try something. Can we come up with an idea on the spot? Maybe a bad idea. So what's a problem you've been abstraction. Okay.
Yeah.
How would you formulate that problem?
Abstraction in state and abstraction in time. Abstraction in time, so I would ask a question like this. Let's say we wanted to make a model of the world. Okay. But we didn't have time steps, because really we don't have time steps.
Okay,
we have continuous time, and the discrete time step is just a convenience. So for many of these cases, you can ask yourself, what would happen? What happens as your time step gets smaller and smaller? Your video gets smaller and smaller. It gets down to 1/100th of a second, or 1,000th of a second, or a millionth of a second, as it approaches continuous time. Things become problematic. You lose. So the obvious example is the action value, the value of an action, Q of SA.
Yes, the Q value, as people like to say.
And as many people have noted, that as your time step becomes small, then the difference between Q, SA, and V of S, the value of the state, becomes minuscule.
Yeah.
And building on action values becomes impractical.
Yeah. So that's a good so very clear
there must be some way
motivation
out of this. Yes.
For why we need action level abstractions. Or,
Yeah.
yeah.
So we should think about Q of SO, which means option.
Okay.
What if I was to behave? So here's a way you could behave. Like, what if, do this action many, many times, forever? Okay, that's a possible option. And it has to terminate. So you might terminate exponentially. So, do this action over the first bit of real time, not discrete time. So the idea of exponentially terminating generalizes to continuous time in the way that the single time step transition doesn't.
Uh-huh.
So you could say, what if I do this action for a while? What will happen? And you could make a model of that. So that would be abstracting over time, action in time.
That's good.
I was noticing there are many instances of this. Like, how are you going to do Q learning? How are you going to do TD learning when you have continuous time, when your time step becomes small? Because TD is all about building on this time step to the next time step. Well, it turns out it's not. As you know, if you use eligibility traces, then you can free yourself from the tyranny of the time step.
Yeah. So now that we're kind of on this topic of options, I did have an options related question for you, and maybe we can build out an idea of how something like this might work. So options, for people that aren't familiar with them, they're exactly what we just talked about, right? They're abstractions over time of taking many actions, or kind of.
They're a policy and a termination condition.
A policy and a termination condition. There we go.
A way of acting and a way of stopping.
Yeah, and generally they're represented, right, in like when you show your representation of the agent, you have like a bunch of different options, and perhaps you could use them to plan or to take actions, use them, enact them in the environment. How would you come up with an option, though, for something that you've never done before? Something like we often like to say, like, okay, we're going to have an option for going to college. Like, obviously, I can't experience that to make the option. How do we get to something like that?
So the recent proposal is that options are feature-oriented. They want to achieve some feature. So you have the feature of tea going into your mouth, or the feature of the image of the Amy coffee cup, and then you want to recreate that feature, and you learn how to recreate it. So you don't want to predict whether it will happen if you're walking across the room. You want to predict, will you get the image of the coffee, of the teacup, if you tried.
Yes.
So,
So I guess if you have some idea of what going to college is and what.
Well, going to college is so cognitive and so large.
Yeah, maybe graduating.
Well, I like picking up the teacup.
Or
going outside, or standing up.
Okay. Well,
these are things you have to decide all the time, or even deciding which way to go in the conversation.
Yeah, but if we're like talking about planning, right? I do like to be able to think of people are able to plan at those very long time scales, right?
So planning is yet another thing. You could have temporal abstraction without having planning. But planning is one of the main uses. So, the order is you form a way of behaving and a way of, and a way of stopping, and then you make a model of it. You say, if I behave that way and I stop in that way, where will I end up? And how much reward will I lose while doing that? And then you can plan with it. So I want to tell you about my thing, my most recent paper, STOMP.
Oh yeah, I've heard the STOMP.
Yeah. I want to tell your audience. So STOMP stands for these four phases. The first, the S and the T are together. They mean subtask. You start with a subtask like getting the tea in my mouth, standing up, or being in college. And so you have the subtask, and then you learn an option to achieve it. And then once you have the option, you learn the model of the option, which is actually much bigger than the option itself, because the model has to say what will happen to everything if you follow the option. And STOMP, S-T-O, for option, M for model, P for planning. Once you have the model, you're then able to do planning.
Yeah, it's good.
So this is the, what do we call it? The STOMP progression for the autonomous development of cognitive structure or something like that.
Yeah, that's a mouthful.
We need to develop cognitive structure. We need to develop other things in our minds, like models and subtasks.
Yeah.
Yeah, no one else is going to.
Yeah.
Well, a few people talk about this.
A couple do.
Yeah.
I think I tend to find that like no matter the subject, there's usually a couple people looking into something interesting.
Yeah.
Maybe not always as many as I would hope, but there's always a good few interesting works. So here's a kind of jumping topics here. I'm not sure if this is off if we're allowed to talk about this. You recently started working with Keen Technologies.
John Carmack.
Yeah. I also messaged him 6 months ago, asked him for a job. He said, well, he actually responded, and I think he said, we're not hiring. So very unfortunate for me. But you started working with him in the company. Are you allowed to say anything about that?
Sure.
Oh, what a welcome surprise. What are you guys working on?
It's all the same things.
Yeah, well, I imagine that they started off working on something kind of different. I mean, they don't really, I think, say anything about what they've been working on. Is it really that similar? Yeah.
John and Gloria and Lucas, starting by fully understanding deep learning, and they do start there. They much more than I do. They start with that's the standard, and then they work out from there into more online learning and reinforcement learning and new ideas. Whereas I say, well, that's a bad place, and I don't really want to start there. It'll distort everything, or maybe because I'm just lazy or ineffective. Anyway, I don't start there. I tend to start more from the linear and then build up.
Yeah.
But really, that's sort of true. But really, I mean, I'm just one guy. I can't do everything. And so what I'm really working on is the ideas of the structure. How is the structure of the agent? How do different parts fit together? And what could the parts be? I don't think they're as simple as, for example, as described in the Alberta plan. We need to, that's just a place, a point in time, a starting place. We need to get more sophisticated understanding of them.
But there is sort of between all of you like a very fundamental agreement about the importance of learning online, being able to do RL, those sorts of things. The things, learning from like normal experiences, the sorts of things that like you tend to value a lot, they also. Are those things you're all aligned on?
What?
So sort of the things that are fundamental to the Alberta plan, right? What? So things like learning from common experience, learning.
It's not exactly the same, totally without the group, which is a good thing. Different points of view. The greatest commonalities are even more basic things, like imagining you might have to think differently from everyone else. Thinking that the code of the algorithm will be not that complex. Not like millions of lines, but something that a single person could probably easily write if they knew what they were doing. So it's all an interest in simple basic principles. A belief that scale can come later. That you need to get the ideas first, and then you scale them. A belief in decentralized algorithms.
Decentralized, as in like?
Well, for example, a system that's presenting a batch of something over and over again is a very centralized algorithm. There's one clock, and there's one thing that everyone's doing.
Yeah.
A decentralized algorithm is more different parts are doing their thing.
Oh, I see what you mean. Modular would perhaps be another word meaning a similar thing.
Decentralized is much better.
Okay. Why is decentralized better? What's wrong with modular?
Well,
I guess because decentralized.
Don't need to have modules.
Yeah, I guess decentralized. Okay, yeah. good point. I guess you don't necessarily need modules. Yeah. Interesting. So are there any projects that are like sort of group efforts, or is it more of like we're working on similar things, we want to share ideas?
So we haven't yet formed a group effort. We're still figuring out how the other is thinking, and trying to figure out where we want to be.
Yeah.
How long have I been there? I've been there since the end of September. So it's just a couple of months, really.
So let's say, sorry, I'm going to switch gears again here. I have like my list of things, and there were a few things I definitely wanted to ask you. So
Good.
I'm trying to get through them now. How much, I've not been keeping track of time.
Don't worry about it either.
Okay, good. So one of them was, let's say we succeed. We as in, I don't know, maybe the community, we make AI that is...
AI scientists.
Yes, AI scientists,
And
engineers, everyone that shares this goal of...
We understand how the mind works, what the basic principles are.
Yeah.
We can make minds.
We can make minds that could do the same things humans could do, or better, or animals.
We really solve the problem.
Yeah.
Good.
So you've expressed your opinions on this. I rewatched a video in preparation for this, and your take, right? Let me make sure I'm getting this right before I go forward. Is that these are sort of our brainchilds? It's the next step of evolution. We should be very happy, excited, proud when this happens, and let them grow, flourish. They'll basically. The way I kind of think about it, as you think of the next stage of humanity, right? They're growing from us, and they'll be better than us, and we should celebrate that. And then we can sort of...
to the extent that they're better than us.
Yeah.
Yeah, we should celebrate that.
Yeah.
It's all part of what's come out from our civilization, human civilization.
Yeah. And then we can step...
This is success.
So it's success to be able to do that. And then we can sort of step back and focus on other things, I guess.
So, I don't know, I think many of us will be trying to move up with them. We'll be augmenting.
Yeah. So that'll be interesting.
But ultimately, we will make things the next way of being, the next most capable, most intelligent beings will be designed. We will partly be designed.
Yeah.
We will be designing improvements.
And
no one can really say exactly how it's going to turn out, but this is not exact. This is just saying, we're going to understand intelligence. We're going to make things that are better, and that's going to happen.
Yeah, and another thing...
And that's good.
Yeah, and another thing I've heard you say, right, is that we should treat them, with all the same rights we would a human, because they would be more intelligent. And if you're going to discriminate and say we should control AI and it should just be like the tools that we use, even if it's much more intelligent, that would be discrimination, right? So here's sort of my question: is this sort of view really paints it as if they are kind of like almost as if they're just better humans, not better in terms of like every which way, but like they're smarter, they can achieve their goals more efficiently. But the sort of missing part for me in understanding your perspective here is like we get to decide what the goals of the agent are, right? There's not they get to decide their sub goals, but the reward function, if this takes the form of RL, is something that
we could. But notice we don't do that with our children.
But they also have some like inborn...
Why don't we do it with our children?
Well, some people do, but I think we could agree that's probably not the best thing.
No, I think that's exactly the point. We think it's probably better not to. Because although we do have some idea, and we try to teach them, and the evolution builds in certain things for better or worse, we do recognize that you can go too far trying to control your children. And it's better for the whole society. It's better for you, in fact. It's certainly better for your children if you don't try to control them completely.
So I think
it will be the same with the machines.
There is like a really core difference though, right? Particularly with the evolution inbuilt sort of reward function, so to say, in that like we're really working with a completely blank slate if we're designing something, right? There's nothing, like there's no reason to believe something we would build would have emotions unless we explicitly encode something that allows for, or that, I guess.
You really think so? You're really
No,
there?
actually, I'm actually going to take that back, because I guess emotions could very naturally come of many different reward functions, right?
You don't think hope is an emotion?
Yeah, that's
You
why.
don't think fear is an emotion?
That's why I'm very quickly backtracking this. I guess I could imagine that sort of
Certainly
thing.
reinforcement learning systems have pain and pleasure.
Yeah. So I guess those do emerge from many reward functions, right? Which is why you would say, regardless.
From any. I don't know if you said.
I
Sounds like you said many.
Of many. So like no matter what.
I'm going to say of any.
Of any.
Yeah.
Okay. So this is perhaps was the missing piece for me. So you're saying no matter what their goals are, whatever we encode them to be, these sorts of emotions that humans feel, or animals feel, I guess it doesn't need to be specific to humans, those sorts of things will arise.
They will have emotions. They be, they could be the same. Like they're still feeling hope, they're still feeling fear. But the things they hope and fear might be different.
Yeah. Would they?
They would be, just as they are for us. Like,
yeah,
I'm fearful. Like if something threatens my life,
mm-hmm.
if less so if something threatens someone else's life.
Yeah, and I guess this. That makes sense to me, but it's not clear. Like, it's probably not clear to me because I don't know how human emotions work. Like, how do we? The experience of emotions. It's like a very. I guess now we kind of dive into consciousness. Like, what does it mean to have a subjective experience? Because you could very much design a system probably nowadays where, agents even now you could say perhaps have a fear of not reaching the goal if they get a negative reward when they don't reach their goal, right?
Fear is a prediction that something bad is going to happen.
So is it just a prediction? That's what I'm trying to get. Is it just a prediction, or is there something more that happens in animal consciousness? I have
animals,
no clue.
These predictions are tied to reactions.
Yeah.
So the trivial one, just to make it seem ordinary and prosaic,
Mm-hmm.
the trivial one is if you think someone's going to poke you in the eye,
Yes.
you're going to close your eye. It's just built in. If you think that someone's going to chase after you and you're going to have to run or fight, then your heart rate will come up. Built in. So that's like an emotion. It's a built-in reaction to a situation which you have predictions about. So if you predict something really bad is going to happen to you, you have other reactions, involuntary reactions.
I'm a little skeptical of accepting the idea that sort of the reaction is that closely, I mean, clearly it's tied to the emotion, but that they're inseparable doesn't seem to be the case. Because, like, if we...
Well, so we're going step by step. We have the fact that things like fear and good things and bad things influence your decisions, and your predictions of them influence your decisions. And now we have that we can also get reactions like freezing and heart rate coming up.
Yeah.
And there are more of them. There's people have mapped out 6 or 8 different emotions, where I've only maybe in a modern reinforcement learning system you only have like 4. There's 2 dimensions: pain and pleasure, and hope and fear.
Okay. So value, function, and reward. Right.
It's all predictions of. Actual rewards, and then hope and fear is value function, predicting good things, predicting bad things.
Yeah.
Feeling good things, feeling bad things.
Mm-hmm.
Yeah. So to me, it sounds exactly like emotion. It's just a very simple set.
So let me make it very simple then. We have, say, take reinforce, like super simple RL algorithm. We have a reward function. We train the network. Does that count as now, what was it? Pleasure and I forget the exact word.
Pleasure and pain.
Pleasure
You're
and
doing
pain.
reinforced, then you don't have a prediction.
Yeah,
So you don't have hope and fear.
but we would still have those two. And would that count for you? Like, are we then, this is why I can't fully buy this, is because if we break it down to like the simplest setting, like the emotions, I don't see where the emotions would be there.
All it has is pain and pleasure.
Yeah, but would we say subjecting like any intelligent agent to pain is like an immoral thing? Then like we would be immoral by running PPO or reinforce, right? And that, I mean, I hope I'm not immoral by running, because I did a lot of PPO runs for my thesis.
So there's a lot of things to unpack there.
Yeah.
The whole notion of many of these things are appearances, and they're no less real for being appearances, and also many of them are a matter of degree rather than absolutes. But short of getting to that, I think it's perfectly appropriate to view them as analogs of emotions, and that the closer you want to look at that, the more it will work out.
But they're like, I'm still very unsatisfied, so I'm going to keep pushing.
So that when we understand intelligence, we'll understand things that have goals and have sorrows and regrets and joys and disappointments. They will have all those things, and so in those senses they will be like us, and they will impact their minds in similar ways. You know, like if something really bad happens, they might be depressed and unable to think clearly. I think that those kind of things will happen. But we may be able to repair them better.
Yeah, but where along the way, from like this simple reinforce example to like this super complex future thing that we develop in the future, where does the emotion emerge? Is it there the whole time?
So it's an error to look for a break point from one to the other, a threshold.
But you're saying
because it's in the eye of the beholder. It's in the eye of the beholder rather than in the thing itself, just like intelligence. Intelligence is the computational part of the ability to achieve goals, and achieving goals is a thing that's in the eyes of the beholder rather than in the thing itself. The thermostat, often for beholders, it's useful to think about as keeping the house warm. But it's all a matter of degree, and it's all in the eyes of the beholder.
Yeah.
So you can't look for, where is it really? There isn't that is not a good. That is not a meaningful question.
It seems like if we can't,
is it really a pain, or is it not? Is it not really pain? No, this is not a useful question. Because we'll translate, describing it feeling pain is really a way of saying it's useful for me to think of it as feeling pain. That's what it means. It doesn't mean, it appears to mean, the thing itself, it's got pain in it. So I want to open it up and see if there's pain. No, all that is wrong thinking. You have to think that when I say it's feeling pain, you say it's useful for me to think of it as feeling pain. That's what your sentence has to translate into. So then you can't say what you said. You can't say, well, when is it really feeling pain? When does it cross over?
So it always is, would be your answer, but
no, it's in the eye of the beholder. So if the beholder wants to look at it more closely, in more detail, he might cease to think of it as being pain.
Okay. So then why, the question, and I think I have the answer to this, but then the question would be, why should we care a lot when we have these more complex systems that are more intelligent than us? And I guess the answer is the fact that they would be intelligent, more intelligent than.
Even intelligence is in the eye of the beholder.
Yes.
Ultimately, the reason will be because we find it useful to think about them as being intelligent. Things having appearances, and the appearances actually being important, rather than just an epiphenomenon, is something we can we should be familiar with. I think of like your computer screen or your phone screen and the icons all over it. You think about the apps, so you know that that's all imaginary. There are no real apps. There's just bits, and they're doing things. But it's useful to think about them as apps, and they're useful to think about them as having a place on the screen. That's a useful illusion. It's a useful appearance. And yeah, everything is like that. Yeah, sorry to get so deep.
No, I wanted to get deep.
We don't really have time to lay that out, but it is the resolution to all these concerns about consciousness and whether or not there's really pain or really emotions and consciousness.
I definitely have to think about it more, but I do think I think I get the high level idea of what you're getting at.
Good.
Yeah.
Good. Next question.
Conscience. Next question. Okay, let's take a peek at what do. I have any? I definitely have more. What else did I have? Oh, I forgot to ask my first question. We're too far past that now. What's your favorite flavor of ice cream? Someone on Reddit wanted me to ask you that.
Chocolate.
Chocolate.
It's got to be super chocolate, like chocolate pudding from Steve Harrell's in Massachusetts. That's the best.
Well, there's some recommendations for anyone in Massachusetts, I guess. I don't know. I don't get chocolate. It's like chocolate ice cream doesn't taste like chocolate to me. That's the problem. Like if I want chocolate, I'm just gonna eat chocolate.
It's just one flavor. That is the best.
Yeah. Oh. I think we need to end it.
I like banana and cinnamon. Those can be very good. No,
that
banana and cinnamon.
Yeah. Okay, separately. Okay. Okay, yeah.
You can have the banana with the chocolate, but don't have the cinnamon with the chocolate. You're just overwhelming.
Okay. I'm sorry, I'll get back on topic. Oh, this was a good one. Do you know Alex Lewandowski?
Yes.
He asked me this question to ask you, and I think it was a good one. And I think you, and me too, view RL as like a very fundamental problem. This sort of idea, I think, what's the exact quote? Intelligence is the ability to achieve, the computational part of the ability, can you say it?
Intelligence is the computational part of the ability to achieve goals.
Yes.
That's what John McCarthy said.
Yes, and you've changed that a little, right?
My version is intelligence is the computational part of the ability to predict and control your sensory input stream, particularly the reward.
Yeah. So here's the question then. Is this view of intelligence, do you think, a universal phenomenon? So if there is alien life,
it is what makes intelligence powerful. It's that it can predict and control signals.
Yeah, I think I probably share the same opinion. So if we were to find intelligent life, and they were also to be designing agents, they would probably also be working on a similar definition, and maybe they'd also be caught up in reinforcement. Do you think they'd be caught up in supervised learning?
Probably. Yeah, there are good reasons for that.
Yeah.
And you do know, of course, that the reinforcement learning research is a consumer of supervised learning methods. Mm-hmm. We need them. We need them.
Oh yeah.
We just wish people would stop saying that's all you need.
Yeah. Yeah. I mean.
Yeah.
Yeah. I have a video on my channel talking about this, and I was very sad. It was one of my very poorly performing videos. I was like, oh, this video is so good. I make this very clear point, and then it didn't do too well. But oh well.
Let's do it again.
I should do it again. I will do it again eventually. I'll keep working on the argument. Yeah. So, yeah. Another thing I wanted to ask you about is sort of your approach to research. My approach to research has very much changed. I mean, I didn't really have much of an approach when I came, considering I only worked on one project, one research project. And my approach was there's lots of these interesting ideas kind of floating out there. I want to basically take them and see how I can apply them to achieve these different things. And that's changed. That is very different from, I think, your view, which is we have some very fundamental problem we want to solve, and we're going to try and find the simplest environment where we can test a bunch of algorithms and see what kind of algorithm works. And then from there, we're going to scale it up, right? So maybe I would love to think of an example of this. So the reward respecting subtasks paper, right? This is all about learning options that respect the reward, that are not completely separated from it, So if like one of your options is perhaps right, like drinking coffee, but then your reward is like, you want to taste good things and coffee this tastes like awful, then perhaps the option would like not always drink the tea, or I said coffee, if it tastes bad, right? I'm not sure if that was the best way of explaining the paper, but.
My favorite example, the same idea, is that you want to get in your car. Mm-hmm. And so, get on your car to drive somewhere. But suppose your car is locked.
Yeah.
If you really are going to get in your car, then you're going to smash the window.
Yes.
And you shouldn't. There should be an option for getting in your car. But if you don't have the keys, you do something else.
I definitely prefer that example. So where's I going with this?
It's the same thing. So you would need, in principle, you have two different options. One to get in your car when you do have the keys. One to get in your car if you really want to smash you really need to get in the car.
Yeah.
It's a life or death. Nothing else matters. And so you need two different options. You want to have the ability to have options that can back off.
Yeah. So, and your approach to solving this problem, though, is of course not building a robot and having it try to get in the car. Your approach to the problem is taking a very simple mini grid problem and then coming up with an example that would prove that this works if it works, right? And then you can try all these different variations of the algorithms that let you...
Ideas matter.
It lets you try all the ideas very quickly. And one thing I've learned that maybe you can help me articulate better is why is it useful? Can you build the case for working in these small environments and then worrying about scale later, as opposed to what seems to be, because when I came
What's the case for this approach that I like?
And I should say, of course, this is not your approach. This is the approach of, I think, many good researchers, but it's been less and less common recently. And I'm not sure it's entirely because people think it's a bad approach so much as it is maybe lots of recent researchers taking really cool ideas on a big scale and just seeing what they can do with it. But I think there's lots of really cool things you can do.
You need both.
Yeah.
But I do feel that the one that I like, the small experiments to figure out a point, has gone out of fashion a bit.
Well, I think maybe one of the best ways to convince people, I am very much trying to convince people now, but what are some cool examples? Some of the coolest examples of maybe ideas that you've seen demonstrated, like very simply, that have ended up being very powerful ideas?
TD,
yeah, that's a
TD paper.
One.
TD paper is a really good example, case in point.
What was the original?
The 1988 temporal difference learning paper. The demonstration of its effectiveness was in a 5-state random walk. Just your 5 states, you go back and forth, 50-50 each way. If you go past the 5, then it ends. And I said, and it was like this when I figured it out. I said, well, to myself, if that's right, then it should make a difference even in a tiny, simple problem, as long as it had some causality and it was going through like a simple random walk. Even there, you should be able to show that it's an improvement. And so then I tried it, and it did show an improvement there, and that was critical to convincing me.
Yeah.
Yeah.
And since then, TD's obviously been used a lot more.
Well, in the same paper, we also talked, you could be using this for backgammon. We did imagine, and then there were other examples, conceptual examples, not worked examples.
Yeah, and I guess maybe another motivator for doing this is you could have easily concluded TD didn't work if you tried it on a problem where you had these sorts of, in a simple MDP or backgammon, like each action makes a very clear difference, right? I guess if you tried it on like a scale where each action, like you need many, many actions to build up to something, it'd be a lot harder to find interesting results, right? Because you're then conflating it with...
The word is targeted. You want an example that's targeted as well as maybe simple.
Yeah.
And if you don't target it, you might not see the phenomenon of interest.
Yeah. And then of course...
So you have to be like generous to your idea. Say, well, if your idea is right, this should be a sufficient place where it will shine. And if it doesn't shine there, so you are giving it, like every advantage.
Yeah. And then from there, I guess you remove these sorts of advantages after it does work, right?
Yeah, you would challenge it more
Then you challenge it.
strongly.
And how, so kind of going back to this idea of scaling being easy, how was it scaling temporal difference learning? Did you need to
I
make a
didn't
lot of
do it.
changes? Well, yeah. Well, but
Jerry
you know
Tesaro
this
did it.
story, right?
Jerry Tesaro did it.
I'm sure you're very familiar with the work. Or
Jerry Tesaro did it in TD Gammon. It was exactly the scaling of TD learning to solve backgammon.
do you know if it needed like lots of,
I don't want to say that what he did was easy.
yeah. Well, there we go.
I don't want to suggest that.
Yeah, so there are challenges to scaling, but I don't know why we can't say they're both hard problems.
I think you're using the word scaling a little bit differently than me.
Perhaps,
Maybe
yeah.
you might be
I think so.
turning it into a useful thing that's important for the world in an application. That's a bigger deal than
Yes.
just making something the same but bigger.
Yeah, that is definitely an important distinction.
So yeah, simple things. Mountain car is a great one.
It is very funny how many, I think, recent algorithms don't work on, actually, I'm not sure that's true. Never
I
mind.
think it's funny that tile coding, linear function approximation, still works so much better on mountain car than deep learning, and that people don't mind it.
Yeah, well, I
It's
mean,
funny.
you are giving like a encoding that works well though, right? There is some sort of human
Yeah, exactly.
element there.
Exactly. You want to have just
Yeah. Go ahead.
the key thing. You want to, in your research and in your research strategy, you want to have clear ideas. I think that's the most important thing. My slogan on my website and everything
I'll check
is,
this one too.
and on my tombstone is going to be "Ideas matter." Now, this is not the list of 10 slogans. This is just
Okay, this
the
is
slogan.
a different
Ideas
one. Oh, the
matter.
one.
And that's the real way to think about me. I think that having a clear idea, pursuing it, chasing it. How you do that? You make simple examples that play this idea against other ideas and tease apart what are the key ideas. Because the theory is there are only like a handful or maybe 2 handfuls of key ideas, and we need to find those, and then we will be able to understand how the mind works. So the big experiments generally don't tell us those big ideas, and they make it much harder to find the ideas because the system is bigger, and we're doing all this additional work other than figuring out the ideas. I think if, as researchers, young researchers, so you and your listeners, you want to find the new ideas that you have already, and you don't want to go learn all about deep learning and all the details of how to do it. Although that may be useful at some point, what you want to do is hold on to the new ideas that you already have, and we each have important ideas. We don't realize that they're new because, well, of course this is what we think. This is obvious to us. What is obvious to you are most likely be your greatest contributions to the field, because something that's obvious to you but not obvious to others will be the source of your greatest contribution. So you don't just want to go learn what everyone else has done. You want to bounce it off a different way of thinking. It was easy for me because I started, as I mentioned, in the 70s, and I was interested in learning. The field was not interested in learning, so I was forced to think on my own. Like, what are the key things? How is learning going to work, and how should it work? And I had to figure it all out myself. So I had a place to stand, and as new things came about, I was saying, well, okay, that could be useful because of this part, but it won't help me with that other part.
Yeah.
And so I had something, a place of my own thoughts to work from. And there's a risk, a downside of the modern field of AI is that there's so much you have to learn how other people thought about it, and and you may have difficulty building up your own first principles place to stand.
I was just going to ask, do you think it would have been actually more difficult for you to come up with the things you did if there were 200 papers coming out a day in the space? Do you think they would have distracted you?
I guess it would depend what they were.
Yeah, because it's one thing I often see all the time, people being like, how do you keep up with this? How do you keep up with like the pace and keep up with what's going on? And I'm always like, well, I don't. I look at some very specific things that I think are interesting, and then a random sampling of some other stuff. It can get very overwhelming, I guess.
Definitely.
I guess that's the importance of focusing, sort of first principles focusing. That's good. That's good. We got some good tidbits right there. Not just tidbits. There's a lot of good stuff there. This is kind of what I actually wanted to go for towards the end. Is the main reason I wanted to do this is I just wanted to talk to you. I thought it would be fun. It's been very fun. So I definitely was right on that. But I'm a very big believer in your way of doing research. Definitely some disagreements too, but like on the whole, I think I've learned so much from the way you do things. I kind of want to convince lots of my audience to look into it very deeply, think about it very deeply. Hopefully lots of them are now interested, pique their interests. So for people whose interests we have piqued, I think lots of the stuff we've talked about will probably be hard to pick up on a deeper level, just because there's lots of stuff we're pre-assuming. Like we both have very similar ideas on continual learning, which is like the focus of lots of these types of ideas, or just these papers we've been talking about. Obviously, we have more context on them. So for people that are more that want to really dive in deeper, where would you recommend them looking? Like, obviously, it's going to depend on the specific ideas they want, but just resources in general.
Well, there's obviously the textbook.
Oh, yes, let me.
The textbook is the thing that I wish I had when I was starting up. And
it is free on your site, by the way.
And it's free on my site.
IncompleteIdeas.net.
And it's written in a friendly way. Everything can be understood. And so I really think that's a good way to learn.
Yeah.
But there's more than what's there. I would just urge you to think about, think classically. It's not so much a new, shiny, techie thing, which sort of deep learning can come across as. It's, for example, this thing we're talking about right now, whether you should look for simple principles or whether you should, what's the alternative? Just keep chasing every shiny thing,
Well, I think
it's more like what we're proposing is like the classical view of science, is that you work on the ideas and you find simple basic principles.
Yeah.
It's all very classical. And in that sense, it will always come back, And also in that sense, I don't feel ownership of it, Like if you were to ask a scientist in another field, and he would say, well, yeah, you want to figure out the essential principles. And a simple experiment. And those are actually much more important. So it's just classical science, and we're trying as best we can to do it.
Yeah, I definitely feel like one thing that frustrates me with a lot of papers I have read recently, is I read them and I'm like, okay, what can I take away from this? And lots of time the answer is either nothing or it's something very, very specific to this specific LLM they're using or whatnot. I've found that frustrating. But that's not to say there aren't lots of good papers too, but it's something I've noticed being very common.
Yeah, let's be generous for a moment. Let's recognize the field has grown enormously, and there's lots of more funding in it. And these are all good things. It's all good for the science. It would be normal in such a case when so many new people have come in that there's some churn and some
something. But it's also good. It's good to have a lot of new thoughts and a lot of new minds.
Definitely we need new thoughts. Yeah.
And then
that's always the most important thing. So that's why sort of we need to be charitable. We need to embrace new ideas. It's like the thing that we're criticizing, to the extent that we're criticizing anything, is that somehow the field has evolved so that it is not open to new ideas. It's like, in order to work here, you have to do the usual thing. And it's like a badge of honor is that I can do the usual thing, and I can do it at scale. You know, somehow it's become like that, rather than like, no, anyone can make a contribution, any size computer, if they're thinking clearly. And that's the way I think. Anyone can make a contribution, just have to start thinking clearly.
Yeah, I think.
And that's I wish the field was more open like that. It was open to new ideas and different ways of making a contribution.
Yeah, that's one thing I hope to highlight soon on my channel. Specifically, I think one really good example of this is some of Kerm's recent work. He's really good at showing these examples where, like, even before this current one, I'll go back to his presentation before that because it's much simpler, is this idea that do bigger networks generalize better? This is an idea that you can test very easily, right? Like, you don't need a 3 billion parameter network. You just need different levels of scale. They don't all have to be big. They can all be different levels of small or medium. And he has some really interesting results there. I might make a video on that. But yeah, I think after seeing a couple examples of this myself, it's a lot more convincing that you can do that sort of really good research without a lot of money and supercomputers. Yeah. You know, one funny thing I saw, this is going back to when I mentioned the RL book I was reading. I was curious what people were thinking about this. I found one post, it was like, oh, this book has ruined an entire generation of researchers. I think it's someone from like control theory. Anyway, funny how different people have such different opinions.
It's interdisciplinary. And yeah, like control theory is one of the big disciplines. When Andy Barch and I were creating reinforcement learning, creating it, reawakening it, that was the big thing to determine. What's the relationship between these ideas and existing fields like control theory? And the control theory guys were always so resistant to new things. And you're seeing more of that with that comment. People saying, well, you're not thinking about it the way that we always thought about it.
Anyway, I just thought it was a funny tidbit. Yeah, this has been good. Is there anything before we wrap up that either you want to ask me, anything you wanted to promote now that you have the cameras? So I have no clue how many people will watch this, but I imagine a couple thousand at least, probably. Maybe tens of thousands, maybe promotion, OpenMind Research.
No, I would just pull together what we've just been talking about and say, you want to think on your own, you want to think from first principles, and the density of the research papers that are coming out in the tiny part of our field, the correct reaction to that is to move out and to go multidisciplinary. Think about how all sorts of different folks from different disciplines have thought about the problems of the mind. So think about psychology, think about animal learning theory, attend the multidisciplinary conference on reinforcement learning and decision making, and maybe attend the upcoming reinforcement learning conference in I think it's August in Massachusetts.
That's exciting.
That's exciting. So insights can come from anywhere. You can all do it. Your greatest potential for making a contribution comes from some idea that you already have, not from some idea you're going to read about. You can do it. It seems impossible. Like, it seems incredibly arrogant to propose that you can have some idea that no one else has had before or can see the benefit of. It seems so arrogant to make a contribution to science anywhere. Even you're doing a master's thesis, you want to make some contribution. Just the idea of making a contribution seems like an arrogant thing. So you can think of something that someone else has never thought of, and think through it more deeply than them, even in a small area, and contribute to the field. But that is the only, anyone can do that. You don't need to be super trained or a genius. You just need to think clearly, and one can make a contribution. Okay, hard work is important too, but there's no special trick to it. Anyone can do it, and that's the way I think about it when I write the book. Try to say things that anyone can understand and appreciate and move forward from. So I hope we can all do that, and I hope we can all do it in a positive way that doesn't like needlessly criticize, but just tries to make progress.
Good message. I like it.
Okay.
On that note, thank you very much.
Thank you, my pleasure.
This has been great. Cut.